I'm Warren Potts, elementary science coach for Winston-Salem Forsyth County Schools. We have Steve Overholt with us and our director, Dave Delayed. Steve Overholt is also with us too. And we're at Petrie STEMtastic Project Lead the Way School in their STEM lab. And I want to thank Mrs. Bailey and Mr. Broom for allowing us to be here and host us as we talk about forces in motion, okay? Hopefully you've already been talking about forces in motion and the different types of forces that are out there. What we're going to do today is have an interactive demonstration of one of our labs that we use in our district. I'm going to stop for you to tell your teacher an answer once I ask a question, or to write in the chat box if you are at home. And we're going to focus on today 5P14. I can predict how increasing the force acting on an object will change the motion of an object. And that's our focus, our I can. It's 5P14. We have it up here too. And in the chat box, write down in the chat box and then tell your teacher who can put in the chat box too, what are our types of forces? Go ahead, put that in the chat box right now. All right. We got a push and pull. And again, also, I forgot to say, thanks for Spees, Ward, and Kano joining us today. I see a lot of you guys putting in, those are your schools. So thank you for joining us today. Awesome. We have some push and pull. Well, great. So let me talk about our lab that we're doing. The unit that we use, the kit that we use in our district for this is the STC Motion Design kit. This is a kit that we've had. This is a newer edition teacher's guide, but the older ones work great too. So this is the materials that you see on the table, except for this little car. And this was just to start talking about how, getting you excited thinking about race cars, hearing the race cars revving their engines. This doesn't come in the kit, but this works with us very well with talking about forces in motion too. These are the materials that come in the kit. These cars, measuring tape, our bookend, string, timers, washers. These are our materials that we use to set up this lab. This is our record, or our data table, a record sheet. Hopefully you may have seen this already, or you have a copy with you. If you don't have your science notebook, hopefully you have some paper to be able to take some notes and write down some questions, because that's what we do. As scientists, we predict, we use models, and we record data on tables and charts. And we're going to do all three of those things today. This is our data table. Our falling weight system is the name of the lab that we're doing today, lesson 3. And so we are going to be putting some washers. These are the washers on a hook, right? And we're going to see if it can move our vehicle in a way, right? In the chat table, in the chat, write down, what do you think? What kind of force would move our vehicle if I put a washer on the hook here and put that over the table, over the side of the table? What kind of force could move our vehicle, right? Put that in the chat right now, or tell your teacher, and your teacher can type that in the chat. What kind of force could move our vehicle if I put it on the hook and put it over the side? What's the type of force? Okay, all right, well, we're gonna look, okay, and that's okay. We're making predictions, we're making some guesses, and that's okay. That's an important part of what we do in science, okay? So we're gonna take a look at that in just a second. Let me move a couple of these other things out of the way here. And something that's very important for us to say too is that our distance is going to be a set distance, a standard distance that we use for all of our trials. And so we're going to have 5 trials that we do. We're going to put different amounts of washers on the hooks, and we're going to see if our vehicle moves. we're going to record notes about what we observe, the motion of our vehicle. How do we see it move? Is it moving in a constant way? Is it moving fast or slower compared to the other trials? Do we see anything that's interesting that happens among our trials? We're looking for all of that. So we'll put our first trial, we'll add one washer, take some notes, right? Also, the time. Our standard distance that we're using, our constant distance that we're using is 60 centimeters. So I measured out 60 centimeters on our measuring tape. And this is 60 centimeters that we have here from the green line to the green line. And this is also going to be great teachers for us to use in later standards or other clarifying objectives and talking about looking at how our vehicle is speeding up or slowing down. So this lab can be used for several different standards and clarifying objectives. Actually, one standard, 5P1, but several clarifying objectives. Okay, so before we start our first trial, and then at the end, we're going to rank these from fastest being number 5 and slowest being number 1. In the chat box, what is something that could slow our vehicle down? Right in the chat box, what is one thing that could slow our vehicle down? And you could also write this in your science notebooks too. All right. We've got some friction. Good. All right. So friction. Friction is something that we have to be aware of. This table is smooth, so hopefully we reduce the amount of friction. There's still going to be friction, but hopefully we reduce the amount of friction. Another area that we need to check before we do our lab is checking our friction of the parts on our standard vehicle. The blueprints for this are in our teacher's guides for this STC Courses or Motion and Design kit. We're going to check to make sure our wheels are running well and that we don't have any rubbing or friction with our parts. So I'm going to back up our vehicle. I'm putting the hook over the side. Do you think, in the chat box, before telling your teacher, will this washer be enough to move our vehicle? Will one washer be enough? Put that in the chat box. All right, we've got mostly no's that I'm seeing. Okay, that's our prediction. Okay, it's okay. We're not grading on our predictions. We are going to write those down and take a look. So we're going to start the video here in a minute. We're going to go ahead and start the video now of us putting one washer on the hook and then see if that is enough to move our vehicle.
Hey, this is our falling weight system. And so we're going to observe our our standard car, being pulled with the hook here that's laying over the side of our table. And it's going to stop when it hits the bookend. And so we're going to see what happens when we add one weight to our falling weight system. So here's our one washer. And I'm going to go ahead and put it on the hook. Double check that we don't have any friction of any of the parts rubbing together. And so now I'm going to put the washer on our hook and make an observation and record. So our vehicle is not moving. I'm going to start our clock too. And now what I'm going to do is just lightly give it a little tap and see if any of the pull of the washer is moving it, and continue to give it small taps. And so really the force is coming from my tap to move it, but there's a little bit of pull on that. And all the way to the 60 centimeters. And so my time was.
All right. Hey, and sorry for a little bit of the technical difficulties, but we're working on this all together. And this is something, luckily, you guys can look at again if you need to review that video, and we shouldn't have some of our issues. But with the first washer that we used, and that kind of force that we were observing was a pull. It was a pull. We were pulling our vehicle was a pull on our vehicle. But it was not enough to move our vehicle without a little push. I was having to push a little bit at the end, okay, just a slight tap from the back to try to move it. And it took 36 seconds and 58 hundredths of a second. That's 36 seconds. It may have felt like 36 minutes, but it was 36 seconds. So we're going to continue to add to our washers. Our second trial is very similar to the first. So we're actually, for time, we're going to skip the second trial, but we still need that data. And so I'm going to put that data on the board, and that's 28 seconds. So please write this down. And 8/10 of a second, or 80 hundredths of a second. That was how our time for the second trial, and it did need some guidance too, with two washers. Now we're moving to adding 4 washers to our hook in our falling weight system, right? Now we've talked about friction with our surface in between parts of our vehicle. There is a little bit of friction too with the string on the table. We've talked about forces, pushes, and pulls. What is the science term for what is pulling down on our falling weight system, on our washers? Write that in the text now. What is the force that is pulling on, the science term of the force that's pulling on our washers, as I put that over the side of the table? Let's see what you got. Gravity, gravity, gravity. Great job. See a lot of people writing gravity. That's awesome. That is what is pulling on our falling weight system. Right. Now we've got 4 washers. What do you think about 4 washers? Will that be enough to be able to pull our vehicle without me giving it taps? Write in your chat box, or let your teacher know, or write it down in your science notebook. Will 4 washers be enough to pull our car now? I saw a couple no's. Maybe I think I see a yes. Maybe do I have a yes? I have a taker for a yes. Okay, so now we're going to move to our third trial, but with 4 washers. We're going to show that tape now.
All right, now we're on trial 3 of our falling weight system. I have put 4 washers at the end. Our last trial, we used 2 washers. I still had to push it on our last trial. So now we're on our third trial, and with 4 washers. And I'm holding the string here, and I'm going to let go. And hopefully you made some predictions on how fast you think this is going to go. And is it going to go without me pushing it? So let's start it. And I'm going to do a little countdown here. 3, 2, 1. All right, and I see that it's still not going on its own, but I'm going to give it a little tap, and we can see that it's traveling a little bit more, a little further on its own with just a little bit of guidance, and tap. All right, I did kind of give it a little bit of a big push there, but for the most part, there was a lot more distance traveled on its own. That was 17 seconds and 6/100th of a second. 17:06. Traveled more on its own. All right. And so we're going to do 2 more trials or tests and so make some predictions now. Are we finally going to be at a point where it travels on its own with a falling weight system from the weights pulling it and moving it across the table.
Now we're going to add 8 washers. All right, and let me pull back up our hook here. We're going to add 8 washers, and we're going to observe that motion too. Now in the chat, we're at up to 8. It's not enough to push it over the edge so that we have a constant motion of our vehicle without a push. Put it in the chat. Yes or no? Is 8 washers enough to go the full distance? All right. Yeses, 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 yeses. Okay, it looks like we have a lot of yeses in our chat box. Make sure you're observing our motion of the vehicle too as it moves. Okay, we're going to show our next.
Hey, now we're back, and now we're with our 4th trial. And now we're working with 8 washers on the hook, pulling our standard vehicle, pulling our Connects car. And so with the use of gravity, pulling on those, and that is our force, is a pull. We're going to see now, is it going to be able to move all on its own without any pushes? Are we going to need 1 or 2 pushes? So hopefully you're thinking to yourself, how many is it going to take? And I'm going to let go of it on 3. 1, 2, 3. And there it goes. 3 seconds. 3 and 3/3 of a second. So that was much faster than when we only had 4 washers. Moved all on its own. No pushes.
You guys were right. Yes, it went the full way without having to have any pushes. It went the entire distance. Our force was changed, and so the motion of our object changed. It increased how quickly it's traveling over our standard, our constant distance, and we're at 3 seconds and 3/100 of a second. All right, now we're pulling out our large washer. Okay, we're going to take off our small washers now and put them in our cup, and we're going to put the large washer on. All right, right in the chat box, make a prediction. How many small washers do you think this equals? So of these small washers, how many does it take to equal 1 large washer? What do you think? Write that in the chat. Put some numbers. How many do you think are those small washers? I'm just repeating if somebody missed that. How many small washers does it take to equal 1 large washer? 3? Good guesses. 16, somebody said. 5? Who said 16? All right. 3, 10. More 3s and 10s. I feel like I'm on some kind of loops. I just keep 3s and 10s. It's pretty close. Actually, if we add the 10 and 3, or maybe just go back to the answer of 16, you're right, 16. It takes 16 of these small washers to equal 1 large washer. Okay, we can prove that by actually grabbing our digital scale, putting them on that, and comparing the 16 washers and 1 large washer. So if this should equal around 16 small washers, now that we're on a full travel now, I'm wondering what's going to happen to this time. In the chat box, right, increase or decrease? Is our time going to increase in number, or is our time going to decrease in number now that I'm adding a one large washer? Okay, so our time, the number that we have is going to decrease, is what I'm seeing. Increase, a couple of increases. All right.
All right, now we're on our last and final trial. We're using the large washer that is equal to 16 16 small washers. And so we're gonna, hopefully you made some predictions, and we're gonna see what happens to our vehicle when we have the large washer on the falling weight, our falling weight system. And I'm gonna let go on 3 and also try to hit the timer. And 1, 2, 3. 1 second and 55 hundredths of a second. That is pretty interesting. All right, so let me record that. And we saw it move really quickly.
All right, now we just completed our last trial. One large washer, and that took 1 second and 55 hundredths of a second. And so that's interesting because that is almost half of our last number. So those of you who said our time is decreasing as it travels a constant distance, you are right. Great job. Our time was decreasing. So now we're getting close to our wrap up. Teachers, you should have some of the resources that we shared, which included a post-assessment survey, Google survey, that talks about this data that we collected on our data table with the falling weight system. There are also some formative assessment probes, which is written by Paige Keeley, and helps us discuss about what we've seen in different things and uncover some of your students' thinking. So some other questions to leave with you. What would have happened if I did not have the bookend to stop our vehicle? Some other questions. Is there some distance? Is there some relationship between our distance from the table to the floor and our distance that we're traveling here? So that's just some other questions to think about. 2, what would happen if we added 2 washers, 2 large washers to, you don't have to put things in the chats. These are just some questions you can write down in your planner or in your science notebook. And again, I hope that you have this data. Your teachers can share this data with you too. Thank you for joining with us today. And if you have any questions, make sure that you let your teachers know and they can email us. I want to leave you guys with some time to be able to wrap up in your classrooms too and connect these forces and motions that we're talking about. Again, our standard was I can predict how increasing the force acting on an object will change the motion of an object. 5P14 with Winston-Salem Forsyth County Schools Science Department. I'm Warren Potts here at the STEM Lab of Petrie Elementary. Thanks for joining us today and have a great day.